we are going to do more calculation under the buffer, preparation of buffer. Now we have the question here that says calculate the pH of the solution formed when 500 centimeter cube of 0.1 mole per dm cube of a weak acid is mixed with 500 centimeter cube of 0.2 mole per dm cube solution of the salt. The Ka was given as this. So if you write out your parameters, in this case, your parameters are, let's take out Ka first. What was the value of Ka? 4 times 10 raised to the power of minus 5 mole per dm cube, right? Exactly. Now, what was the concentration given? Concentration of the weak acid. The weak acid, HX, was given as 0.1 mole per dm cube. Are you getting it? Now, what was the concentration of the salt? The concentration of the salt of the weak acid, which we can indicate with X minus, was given as 0.2 mole per dm cube. Their individual volume, 500 centimeter cube, 500 centimeter cube. Now note something. What is the formula for pH? My dear student, we said pH is equals to pKa minus log of acid over salt, right? Now, how do we calculate for the pKa? pKa will be equals to minus log, Ka is 4 times 10 to the power of minus 5 mole per dm cube. Alright, so that pKa would be equals to minus log 4 times 10 raised to the power of minus 5, which is 4.39. 4.397. Alright, so our pKa now would be equals to this. So how do we calculate for the pH? But note something, there's something I want you to take note of here in this question before we continue. You know when you miss the two, because you are going to miss 500 centimeter cube of this 500 centimeter. Now what do you think will be the total volume of solution formed? 500 centimeter cube plus 500 centimeter cube will give us total 1000 centimeter cube. Now you now see that the volume now is twice the initial volume of the individual components. The individual component in this case, the volume is twice the volume of HS and twice the volume of what? X. Is that okay? So how do you do this? The concentration, if you increase volume, what do you think happens to the concentration? Will it increase or it will decrease? Of course, the concentration will decrease, right? It's just like you are having sugar, or you cook food and there is enough salt inside. If you add water, what do you think? If you increase the volume of the food, do you think that the sugar will still be much inside of the soup or it will decrease? Of course, it's going to what? It's going to decrease. So increasing the concentration, mixing the two solutions together will what? Will lead to increase in the volume and definitely a decrease in the concentration. But in this case, the initial concentration, the initial volume was 500 centimeter cube. Are you getting it? The final volume is 1000. So it means that you increase the volume times 2. Hence, the concentration will be decreased by 2. So this concentration of 0.1, you now divide it by 2. Since the volume increased by 2, concentration must what? Decrease by 2. So this will now be 0.1 divided by 2, which the concentration of this new one will now be 0.05 mole per dm cube. This one also, the concentration will decrease, and this one will give us 0.1 mole per dm cube. What is responsible for the decrease in concentration? Because the volume was increased. The missing increased the volume times 2. So these concentrations here is now what you are going to use for your solving. These two concentrations here are not this one. So if we now come to our pH formula, pH, pKa was what? Was calculated as 4.397. So we have 4.397 minus log. Now HA is equals to HX, which is the acid. The acid is the HS. Concentration is 0.05 mole per dm cube. Now the new concentration 0.05 mole per dm cube divided by 0.1 mole per dm cube. All right, so that at the end of the day, what do you think you are going to be having? This we cancel this, and then you are going to have pH will be equals to 4.397 minus log 0.1 rather, not 0.01, 0.5 rather. All right, you can press it. 0.05 divided by 0.1, it's going to give us 0.5. So you now have minus or log 0.5. What did that give to you? Minus 0.301. So pH will be 4.397 minus bracket minus 0.3010. So pH, when this multiply this, is going to give us positive. So 4.397 plus 0.3010. All right, so 4.397 plus 0.3010, which is going to give us 4.698. So our pH will be 4.698. All right, that was how you got 4.699 in your material. You can see it there. It's approximate 4.698. Is that okay? So you see that it's a very simple something to go through, just for you to know what you are doing. Is that fine? All right, let's see the next one quickly. Preparation of buffer solution. Now, how do you prepare buffer solution? There are 3 steps to follow if you want to prepare buffer solution. Now, the first step is that you should choose a suitable weak acid or a weak base, whose emphasis on this pKa or pKb is almost close to the required pH of the buffer solution. So if you are looking for a buffer with pH of, let's say, 4.7 or let's say 5.0, you should choose a weak acid or weak base that has a pH that is close to that of the buffer solution you need. Now you now calculate the ratio of the concentration of acid or base to that of the concentration of the salt. That means what ratio of the acid are you going to mix with the salt that will give you the required pH? Are you getting it now? Or the buffer that you need. Then you add the required amount of the salt to the acid or base as determined by step 2 above. When you have calculated the ratio or the amount of the acid, you know a buffer consists of a weak acid and its salt, a weak base and its salt. So you need to calculate the amount of the acid and the amount of the salt that will be required, or the amount of the base and the amount of the salt that will also be required. Is that okay? When you've calculated these two, then you are now going to add the salt to the what? Acid or the base as determined by the step 2 above. So now a question says, explain how you will prepare a buffer solution of pH 5.2. Now what was the idea? The idea is, first we have to determine what acid, weak acid we are going to use. Now let us use ethanoic acid, because the pH of ethanoic acid is 4.74, which is very close, pKa rather. So ethanoic acid, we are going to choose ethanoic acid as the weak acid we are going to use. The pKa of ethanoic acid 4.74. So this is what we are going to use. Now we now need to calculate. The pH was already given to you as 5.2. Now, of course, you know the salt of ethanoic acid is sodium ethanoate from what we have done. So the salt will be sodium ethanoate. Now we need to calculate the ratio of the acid to the salt. How do you do that? Use the Henderson-Heisenberg equation. Now the Henderson-Heisenberg equation states that pH is equals to pKa minus log of the acid divided by that of the salt. All right, divided by that of the what? Salt. Is that okay? Now, my dear students, at this point in time, what do you think we can now do? So pH will be equals to, what is the pKa of ethanoic acid? 4.74 minus log. What is the concentration of the acid? This ratio is what you are looking for. So you don't need to substitute anything here. You are looking for the ratio of the acid to the ratio of the base. Now, how do you do that? You just write it, ratio of acid, not to base, to the salt. Now, what was the pH that you of the buffer you need to prepare? 5.2. Is that okay? 5.2. Now, at the end of the day, what do you think we can actually do? We can take this one to this side, so that if this negative crosses here, it becomes positive. So you have log concentration of acid all over the concentration of the base is equals to 4.74 minus 5.2. All right, now you are now going to have log, let me use this, acid over concentration of base, 4.74 minus 5.2. 4.74 minus 5.2, what would that give to you? Minus 0.46. All right, now how do you get acid over base, this ratio? How do you get this ratio? You find the antilog of both sides. So indicate it, find antilog of both sides, my dear student. So if you find the antilog of both sides, what would this give to you? To be antilog, we cancel this log from here. So you have acid over base. Because when you talk about antilog, you are talking about something fighting against logarithm. That's what the antilog is all about. So this will be, and it's the same thing as 10 raised to the power of anything. So this will be 10 raised to the power of minus 0.46. Is that okay? 10 raised to the power of minus 0.46. So at the end of the day, acid over base, the ratio of the acid to the base, you are now going to press 10 raised to the power, antilog is the same as 10 raised to the power of, or you can press shift log to still give you 10 raised to the power of anything. 0.46, that will give us 0.346, which is 0.35. So that was how that answer in your material was gotten, 0.35. Is that okay? Now you have another question here. Now you have another question here. For this particular question, you might not be able to solve. Okay, this is the same question. This one 9.5, because you are not giving the pKa of the compound to use, and you are supposed to be giving the pKa of the weak acid you should use in order for you to apply this formula and then solve it, and then solve it here. So you may not be able to. Now let's look at some of the theory and application of buffer system. Now the buffer are important in the proper functioning of the cells and the blood. I believe you'll be taught the blood transportation in the body, how they bind with hemoglobin and so forth in physiology. Now the buffer, they are very, very important in the transportation of this blood, and they also help to maintain the pH of the blood close to 7.4. Like I have told you before, that one of the most important buffers in the body is a carbonic acid buffer, and the carbonic acid buffer form carbonic acid from carbon dioxide. Carbon dioxide and water gives us carbonic acid. This carbonic acid now act as a buffer with sodium hydrogen bicarbonate in the body, which is an important buffer system that restores the body to a pH of approximately 7.4 plus or minus 0.05. Is that okay? So the most important thing is that the pH in the buffer in our body or in our biological system help to maintain the pH of the blood, so that we will not experience what we call alkalosis or acidosis or systemic acidosis. All right, there are medical conditions that we are taking into cognizance. So I think that is everything Then the next thing you have there is theory and application, chemistry in action, maintaining the pH, how the blood maintain the pH of the body. Are you getting how the pH of the blood is maintained? I've explained something like that before, right? Exactly how the bicarbonate ion chop up the proton, and then carbonic acid chop up every other thing. I think all this one is something that you can read and understand. All right, so that is the end of the entire material. Thank you very much. I believe you enjoyed the entire process. See you in the next one. Bye bye.